I'd like to work through with you a problem about atmospheric air mixtures, problem 1236. And this time, I'd like to show you how to solve the problem using the psychrometric chart instead of that very laborious, complex method that I used the first time using steam table properties. And try to show you, if you have a good working understanding of the psychrometric chart, then you can really get to some solutions pretty quickly. So let's go ahead and get started. So this is problem 1236, except we're going to get properties using this psychrometric chart that I've shown a little screenshot of here. And just let's refresh your memory a little bit. Hopefully you've worked a couple of problems with the psychrometric chart where the x-axis is called dry bulb temperature, or basically the temperature of the mixture, the dry air and vapor mixture. The y-axis is the humidity ratio, kilojoules per kilogram of dry air. But there's all kind of other curves involved in this chart. One of those curves that you can learn pretty quickly is relative humidity. And then there are some other curves that we'll look at in more detail, and you're going to find that, man, those can be extraordinarily valuable if you know how to use them. So let's look at the problem statement first, refresh our memory about the problem statement about problem 1236. It says air at 12 degrees C in 1 atmosphere and 40% relative humidity. That's the clue that it's a mixture of air and vapor. Enters a heat exchanger with a volumetric flow rate of 1 cubic meter per second. Okay. A separate stream of dry air enters at 280 degrees C, 1 atmosphere, with a mass flow rate of 0.875 kilograms per second and exits at 220 degrees C. It's cooling off, heating up that mixture, that atmospheric air mixture. It says, neglecting heat transfer between the heat exchanger and its surroundings, the pressure drops of each stream and kinetic and potential energy effects determine the temperature of the exiting moist air. And again, the clues, hopefully you've looked at this, the very involved solution that I presented before, keywords and clues. You're satisfied that keyword heat exchanger, you've got an open system operating at steady state, steady flow. And for this one heat exchanger, there's 2 inlets and 2 outlets. It says the heat exchanger, it's fully insulated, so there's no heat transfer between the shell or the vessel of the heat exchanger and the surroundings. And of course, the heat exchanger is not lifting a weight. A shaft is not coming out of the heat exchanger, so no work or power is involved with this problem. One of the streams is plain old ideal gas, dry air, that you've probably attacked and have solved numerous problems since about the 3rd week of class. And the second stream is moist air, a mixture of dry air plus water vapor, and the assignment is to find the exit temperature of the moist air. And in solving this problem using steam tables and purely using fundamentals, this became a very involved, difficult problem. So as a reminder of the sketch, here's our basic sketch. It's an open system, steady state, steady flow, 2 inlets and 2 outlets. The streams do not mix with each other. They're totally separate, and all they do is interact thermally by way of heat transfer from one stream into the other. Even though there's no heat transfer from the heat exchanger shell or vessel to the surroundings. Well, let's see. There were 2 approaches, and this is the approach. This is the preferred approach for this solution using the psychrometric chart. What I want to do is break our heat exchanger into 2 separate steady state, steady flow, 1 inlet and 1 outlet open systems. So we've got the hot, dry air open system, 1 inlet, 1 outlet, steady state, steady flow. And we've got one open system with the air vapor mixture, steady state, steady flow, one inlet, one outlet. And so we've got heat transfer from the hot dry air system into the next system, open system of the mixture. So if we write the first law of air, the simple high level first law energy balance for both of them. So for the hot dry air, we've got Q dot in, expected to be a negative number, minus W dot out, 0, equals M dot 1 times H2 minus H1. Okay, pretty easy. You should see an immediate way, immediately in your experience, you should see how to find the heat transfer into negative hot dry air. Now, okay, and so for the air vapor mixture, same approach, Q dot in to the moist air minus W dot out, 0, equals M dot 3 times H4 minus H3, where those are going to be the enthalpies of the mixture. Okay, so I think you're in pretty good shape on understanding the basics of this problem. All right, so here's going to be our solution approach. First thing we'll do is determine the heat transfer from the hot, dry air into the mixture. And we've sort of already done this in the very involved process, but just as a reminder, we've got Q dot in to the hot, dry air minus W dot out, that's 0, is M dot times H2 minus H1, which is the integral M dot 1 times the integral Cp dt. We're going to say that for this hot ideal gas, we've got constant specific heat since the temperature change is really pretty small in the whole scheme of things. And so we'll look up C sub P for the hot, dry air within our temperature range, and we're going to get the heat transfer is M dot times C sub P times T2 minus T1. Pretty straightforward. Okay, next thing we'll do is then we're going to focus on the moist air stream mixture, figuring that we've already got a value for Q dot in, okay? We'll quickly study this particular open system, and we've got one inlet, one outlet, but do you see that we've got to deal with two substances at states 3 and 4. We've got to deal with dry air, and we've got to deal with vapor. And so it's a little more complex. And so think through, how about dry air flow? Doesn't it common sense tell you that M dot 3 of the dry air has got to exactly match M dot 4 of the dry air since it's steady state, steady flow? Same thing on the vapor. M dot 3 of the vapor has got to equal M dot 4 of the vapor. What goes in must be coming out. They've got to be identical. And so we're going to simplify our nomenclature to say we've just got M dot of the dry air, since they're the same at 3 and 4, and we've got M dot of the vapor, which are the same at 3 and 4. Let's refresh our memory on humidity ratio omega, defined as M dot vapor over M dot of the dry air. And so you can satisfy yourselves that omega 3 equals omega 4. Humidity ratio is constant. So for this process 3 to 4, this is a constant humidity ratio process. If you remember from that very detailed solution, and also looking ahead a little bit, we needed and will need M dot of the dry air. We're going to need to figure out what is M dot of the dry air. And remember, you were given the volumetric flow rate, not the mass flow rate. And so to get to the M dot of the dry air, you're going to take the volumetric flow rate of the mixture and divide it by the specific volume of the dry air only, V3 of the dry air. So I've made a little note here. We need M dot dry air, and so therefore we need little V3 of the dry air. We're going to be able to get that easily using the psychrometric chart instead of doing computations. Okay, so let's study. Think in your mind about your psychrometric chart and hopefully some experience you've got so far. If you've got T3, the dry bulb temperature, and the relative humidity phi3, it is a simple matter to find the state of that data pair. If you've got the state, you can easily find the humidity ratio omega. Also, if you've got the state pinned down, you can easily find V of the dry air on the psychrometric chart. I'll show you how to do that. If you've got V of the dry air, it's an easy matter then with the volumetric flow rate to calculate m dot of the dry air in kilograms of dry air per second, okay? Since we've got the state pinned down, we have T3 and Phi3, the relative humidity, it's easy to find the enthalpy of the mixture, H3 of the mixture, and the units of that on the psychrometric chart are going to be kilojoules per kilogram of dry air, not just kilojoules per kilogram of dry air. Now, once we will have calculated Q dot N from the hot dry air stream, so we can write the first law for the mixture, and we're going to be able to solve for one unknown, H4 of the mixture. And once we have H4 of the mixture, we can combine that knowledge, that value, along with the value for omega, the humidity ratio, and those two properties are going to give us everything we need to determine T4. You're not going to believe how quickly this is going to go. Okay, and so here's a statement of the first law for our moist air mixture. Q dot into the moist air, we've got a check mark. That's going to be easy to find. Minus W dot out, 0. M dot of the dry air, that's going to go pretty quickly. We're going to find that quickly. Times H4, don't have, and H3 we can get from the psychrometric chart. The only thing to be aware of here is watch out for units of H4 and H3. This is H4 of the mixture, H3 of the mixture, and recognize that these enthalpy values using the psychrometric chart has units of kilojoules per kilogram of dry air, kilojoules per kilogram of dry air. And that's why it's going to be important for us to work with m dot of the dry air. And so you do see here, we've got m dot of the dry air. We can solve for one equation or one unknown. For H4 of the mixture is simply going to be this expression. And then once we get a value for H4, we're going to go to the psychrometric chart and immediately discover what T4 is. Because a reminder from the third week of class, two independent properties fully define the state of any substance or mixture. Okay, so let's get that heat transfer into the moist mixture first. And so this is from process 1 to 2. I wrote down T1 and T2, turned that into degrees K so I could look up C sub P in table A20. And so I've kind of eyeballed between 500 and 550 degrees K, and I've just put in a value of CP as 1.03 kilojoules per kilogram degree K. R for air, I happen to remember that off the top of my head. It is R bar over the molecular weight, but R for air is 0.287 kilojoules per kilogram degree K. And so given all that, we can determine the heat transfer into the mixture is minus the heat transfer into the hot dry air. So we've got Q dot into the hot dry air is negative 54.075 kilojoules per second or kilowatts. And so therefore Q dot into the moist air is 54.075 kilowatts. That's almost going to be the hardest part of the computation. All right, let's go to our psychrometric chart and start picking properties off of that. Okay, here's what the first thing we do is we pinpoint our state with a dot. We've got air, atmospheric air at 12 degrees C, that's the dry bulb temperature, and 40 degrees relative humidity. So we're going to go to 12, so at least we know we're on this vertical line here at 12 dry bulb temperature. And then where do we put the dot? Well, we see that we've got relative humidity curves that are swooping upwards, and I've got 10, 20, 30, 40, 40%. And so my point, my state has got to be on this 40% relative humidity curve. So there's my dot, there is my state. So you put a little dot there. We've pinpointed the state, the ingoing state, that's state 3. Next thing we do is get the humidity ratio, and we need to just write that down on a piece of paper or our solution. So there's our point we just found. We're going to go across horizontally to our humidity ratio axis, and it's pretty easy. We just write down omega as 0.0035 kilograms of vapor per kilogram of dry air. It's important to write the units down in addition to the numerical value. I'm just going to write that down. I know I'm going to need that. Okay, the next thing, let's get the specific volume of the dry air at state 3. How are we going to get that? Well, here's our point. There's our little point. We need to study our psychrometric chart, and we see another set of axes labeled specific volume. And let's look at the units here. Cubic meters per kilogram of dry air. So those units are very important. And numerically, what have we got? Well, we've got these kind of straight lines that are swooping down. Here's a V of 0.9, a V of 0.85, a little V of 0.8. And so at least we see we're somewhere in between 0.80 and 0.85 cubic meters per kilogram of dry air. And so I had to study on this. So each one of these lines represent 1, 2, 3, 4, 5. Each one of these swoopy straight lines that's swooping down, each one is 0.01. So what I've done is very carefully with my calibrated eye, I'm saying V of the dry air is 0.0812 cubic meters per kilogram of dry air. 0.812 cubic meters per kilogram of dry air. And I need to write that down on my solution too. Okay, now let's work on the enthalpy. So I'm on my psychrometric chart. I'm going to look at this axis label over here. It says specific enthalpy, that's little h, of moist air in kilojoules per kilogram of dry air. So very interesting units, kilojoules of mixture per kilogram of dry air. So you got to be very careful about that. But again, here's our dot. So we'll study on these sort of straight lines swooping downwards, and we'll read off that H3 of our mixture, moist air mixture, is 20 kilojoules per kilogram of dry air. So I'm going to write that down in my solution as well. Okay, and now I've got to put pencil to paper and start doing a little mathematics, okay? And so here, let's see, I've got Q dot N from previous work. I've got AV3, the volumetric flow. I've got to write that down, 1 cubic meters per second. I found that V3 of the dry air is 0.812 from my psychrometric chart. So immediately I can find M dot of the dry air is 1.231 kilograms per second. So here, M dot of the dry air is volumetric flow rate divided, which is 1, divided by little v of the dry air. Okay, 1.2315 kilograms per second. Okay, H for your mixture, I wrote that down. So then, in my first law, one equation and one unknown to solve for H4 of the mixture, 63.91. There it is. So that's from the first law. I back solved for H4 of the mixture. Now I'm going to go back to my psychrometric chart. So I've written 63.91 on a little piece of paper. So I've got to find, okay, so here's my point. Remember that early on in the problem setup, do you remember we said that omega 3 equals omega 4? Okay. And so, well, here's state 3, and I guess I should have labeled this black dot state 3. But do you see that state 4 is going to have to be somewhere along this horizontal line, which is the same omega value? Horizontal line's got to be constant omega, right? I'm going to find my enthalpy on my specific enthalpy axis. So I picked 64 here, and then recognize that I've got to be on this line. I've got to be on this straight line that swoops down So here's a dashed line. So I've got to look for the intersection of my H line and my humidity ratio line, omega. And there it is. I see it with my eyes. The intersection point is almost off scale, but there it is at 55 degrees C. So this is state 4. So I should label that state 4. My little dot, or state 3. But anyway, the big conclusion, the final result, graphically, 55 degrees C. Wow, that really went fast. And so the beauty of this psychrometric chart is that it can just be a treasure trove of properties associated with air, water mixtures at 1 atmosphere. So this psychrometric chart applies only to a pressure of 1 atmosphere. That's an important thing to remember, which is the problem we had. And so can really save you a lot of time from solving these type of mixture problems analytically using the steam tables. Okay, so let's recap what we did. We started with a sketch. We always start with a sketch no matter what. We planned our work. We took some, before jumping right into the psychrometric chart, we planned our work with some knowledge of the way the psychrometric chart works. We started with the fundamentals, so we didn't start with any special formulas. We really started from fundamentals, first law of thermodynamics, and then understanding of volumetric flow rate versus mass flow rate. Those were about the only 2 fundamentals we used. And then recognizing that blindly using formulas is a losing proposition. You might be able to solve homework problems by being given formula after formula after formula, but that does not prepare you to perform well in a quiz or a test or an exam. So blindly using formulas on homework, so that's a losing proposition. And for this particular problem, understanding the units associated with the psychrometric chart, so really studying the psychrometric chart relative to what the units and properties are, that can really pay off for you. In looking ahead toward quizzes and tests, your instructor may instruct you, I want you to solve this using the psychrometric chart. So therefore, you got to get good at it. Instructor might say, I need you to not use the psychrometric chart and use an analytical approach, or you may be free to use either. You do have to remember that psychrometric charts only apply to system pressures of 1 atmosphere. So that's another key thing to remember. So I hope that helps you see and compare how to solve what could be a complex problem a little easier. So there's multiple ways to approach the same problem and solve the same problems, but you're always using the same fundamentals. No matter what approach you might take, you're always using the same fundamentals. And the thing that I thought was kind of cool to demonstrate using these 2 approaches, analytical approach using steam tables compared to psychrometric charts, we got pretty darn close. Psychrometric chart, we didn't exactly get to the 3rd or 4th decimal place, but we got plenty close for engineering, design, and analysis. So hope that helps, and hopes to give you a better understanding and appreciation of how to use a psychrometric chart.